I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on curved mirrors, drawing ray diagrams, and doing calculations for convex and concave. In this video, we're going to talk about curved mirrors, drawing ray diagrams, finding the focal length, and using equations to do calculations for convex and concave mirrors. So first, let's talk about spherical mirrors. So we have two types of spherical mirrors we're going to talk about. One being a concave mirror, which means the shiny side is kind of pushed inward. And the other type of spherical mirror is a convex mirror, which means the shiny side is kind of bowed outward. So we're going to start with image types that are formed from these mirrors. So we have a real image or a virtual image are our options for images that form. And a real image is formed by the converging rays of light that intersect on the same side as the object is placed. So what that means is there's no image that's formed in the mirror. And so you're going to need a screen in order to be able to see the image that forms so that you can project it onto a screen. Now, a virtual image is formed by diverging rays of light. That means that they don't intersect on the same side as the object, which means that we, just like in a plane mirror, we'd extend those rays of light back into the mirror, and where they intersect, that's where the image is formed. So what we're actually going to see is a reflection in the mirror, so you'll actually see an image in the mirror. Let's talk about some vocabularies, the parts of a spherical, concave, or convex mirror. So with the mirror, we can see that we have a nice big sphere, so it's part of a spherical mirror. And if we draw a line that goes straight through the middle, through the diameter, that's known as the principal axis. Now, we also have a point that's right in the middle of the sphere, which is the center of curvature. So it would be the center of our circular or spherical mirror. And when we have parallel rays of light that come in parallel to the principal axis, when those rays of light reflect off, they all reflect through the same point. And that point that all the rays of light parallel to the principal axis reflect through, that point is known as the focal length. So the focal length is the point where parallel rays of light reflect to. Now the focal length values exactly 1/2 the length of the radius of the spherical mirror. So the radius would be from the center of curvature to the mirror. So the halfway point between the center and the mirror is the focal length. So we're going to talk about drawing the ray diagrams for spherical concave mirrors first, then we'll go to convex. So we know that the ray of light that travels parallel to the principal axis is going to reflect through the focal length. Now this is going to be the same as if we were to draw a normal line perpendicular to the mirror and the incident angle equals the reflected angle. It's just noting that a parallel ray of light hits and reflects to the focal length. It's going to be a little bit easier than drawing the normal line each and every time. Now we can draw a ray of light that goes through the focal length, and that's going to reflect off going parallel to the principal axis. So a ray of light that goes through the focal length reflects off the mirror parallel. Again, incident angle would equal reflected angle, but knowing these rays of light makes drawing our ray diagrams a lot simpler than having to use a protractor to measure angles and draw a normal line. Now, a third ray of light is a ray of light that goes through the center of curvature. That's traveling right along the normal line. So that's a 0-degree angle, so it's going to bounce back off of the mirror directly in a straight line, because incident angle being 0 means the reflected angle is going to be 0, so it's going to bounce straight back through the center of curvature. A fourth ray of light that we could draw is a ray of light that hits right at the principal axis. And if we draw this ray of light, we'd have to measure an angle because the principal axis now acts as the normal line, so it's going to reflect off at the same angle. This is going to be a lesser ray of light that we would draw because we need a protractor to measure it. And for the AP Physics 2, you're only given a ruler on the AP exam. So the first 3 rays of light are a little bit easier to draw using only a ruler. Now, the thing to remember is that there are countless numbers of rays of light. So we could draw any ray of light that hits the mirror, not in any relationship, and we draw the normal line, and the incident angle is going to equal the reflected angle. Now again, we need to draw a perfect normal line, and we'd have to be able to measure that angle so the incident angle equals the reflected angle. So it's probably just a little bit easier to draw the rays of light that we know bounce off parallel or through the focal point or through the center of curvature. So let's talk about locating an object. So if we take an object and we place it outside the center of curvature, that means it's further away from the mirror than the center of curvature. We can locate that image by drawing our rays of light. So we have one that goes parallel that reflects through the focal length. We can draw our second ray of light that goes through the focal length and reflects off parallel to the principal axis. We draw that third ray that goes through the center of curvature, and you can see that all three rays of light intersect at one point. So that's where our image is going to form. This is the converging rays of light, which means that this is going to be a real image. So the image is real, which means we need a screen placed right at that location in order to see the object. What we also know about the image is that the image is upside down or inverted. And we also know that it looks like the image is smaller or a reduced size. So these are the properties. If you're asked about describing the image, you talk about real versus virtual, inverted versus upright, reduced or larger or same size. So locating an image at the center, we're going to draw those same rays of light. So we're just going to draw two this time. You can see that they intersect where the object would be in the same spot where the image forms. Now again, we have converging rays of light, so that means that our image is real, so we need a screen to be placed there to see the image. It's inverted because it's upside down and backwards, and it's also the same size. So this is the only location where the object and image are going to have the same size. Now, as that moves closer, we get in between the focal length and the center of curvature, drawing our ray diagram to locate our image. We can see that those rays of light still converge, and we can see that our image is still a real image because we need a screen, that it's still going to be inverted, but this time as it got closer, it is now getting larger. So the image is larger than the object as the object approaches the focal length. Now what happens when it's placed at the focal length? So let's go ahead and draw our ray diagram. So it would be hard to draw the ray through the focal length, so we're going to use the one that goes through the center of curvature instead. So we're going to draw that ray of light from the top that goes through the center of curvature. You can see those rays of light reflect off and they look pretty parallel, which they are parallel, so it doesn't matter if I continue them or extend them behind the mirror, they're never going to intersect, so there is no image that forms. So when an object is at the focal length, there is no image that forms. Now, if the object is in between the focal length and the mirror, we can draw our ray diagram again, drawing those same two rays of light. We can see that those rays of light are not going to intersect on the side where a real image would form. So what we're going to do is we're going to extend those rays of light back behind the mirror so we can locate where our virtual image is going to form. So we can see that where the rays intersect, that image is virtual because we can see it in the mirror. It's upright because it's oriented the same way, and it's larger, so it was magnified. Now, this type of mirror that you would see is, you may have seen a mirror like this in a hotel where you have a separate mirror attached to the wall that has kind of a light that goes with it. And when you look in the mirror, your image is magnified a little bit. And this is the type of mirror, it's a concave mirror, and your reflection, your face is actually inside the focal length, which is what causes it to have a larger image. Let's recap concave mirror images. So if the image is real and inverted when the object is placed outside of the focal length, further than the mirror distance to the focal length. But we know that there's some properties that the image is smaller than the object when the object is outside the center of curvature. We know that the image is the same size when it's placed at the center of curvature. And we also know that the image is larger than the object when it's placed between the center and the focal length. If it's placed at the focal length, no image is formed. And if we place it inside the focal length, we have a virtual image that's larger and upright for our object. So let's look at a convex mirror. Now, a convex mirror, if we look at the convex mirror, the center of curvature is going to be on the opposite side. It's not going to be on the shiny side, which means that our focal length is going to, again, be halfway between the mirror and the center of curvature. And because it's not on the shiny side, this is a virtual focal length. So rays of light aren't going to actually pass through the virtual focal length. So let's place an object in front of that mirror. And we're going to draw rays of light. So we'll draw the one that goes parallel, and it's going to reflect, and it's going to line up with the virtual focal length. It's not going to actually pass through the virtual focal length. We can line one up going through the virtual focal length. It reflects off parallel. And then we can line up a ray of light that lines up going through the center, and it's going to bounce straight back because it's still along the normal line. Now you can see that those rays of light are not going to come together, so they're diverging rays of light. So what we're going to do is we're going to extend the rays of light that reflect back through into the dark side of the mirror. And we can see they intersect, and we have the image is going to form there. And our image is a virtual image because it appears in the mirror. It's upright, but it's smaller. So this type of mirror you use a lot if you drive a car. The passenger side rear view mirror, where it says objects in mirror are smaller than they appear. Well, this is a convex mirror that's used so you can see a little bit further out than if it was just a plane mirror, or even better than if it was a concave mirror. So you get a wider range of view. You also might have seen this if you come up to an intersection and there's a hard to see around the corner. You might see a mirror that's posted across on a pole so that help you see around the corner. That's going to be a convex mirror as well. So we know for convex mirrors, the image is always going to be virtual, it's always going to be upright, and it's always going to be smaller. So there's really only one ray diagram for convex mirrors. So let's transition to calculations now. So let's look at what's called the mirror lens equation. And this works to help find the object distance if needed. So 1 over the object distance, and that can be measured in meters or centimeters. And 1 over the object distance value is always going to be a positive value. And then we can add the inverse of the image distance. Again, it can be measured in meters or centimeters as long as it has the same unit of measurement as the object distance. This value is positive for real images, and it's going to be a negative value for virtual images. And adding the inverse of both of those is going to equal 1 over the focal length. And again, the focal length can be measured in meters or centimeters as long as the values are the same as the image distance and object distance. Now the focal length, much like the image distance, can be positive or negative. The value is positive for a real focal length. That would be for a concave mirror, where the rays of light actually pass through the focal length. And the value is negative for a virtual focal length, which is going to be a convex mirror. Now the magnification equation, the negative of the ratio of the image distance to the object distance, that's going to equal the negative of the image height over the object height. And that value gives us the magnification, which is capital M. Now, some properties of the magnification is if the absolute value of the magnification is less than 1, that means the image is smaller than the actual object. If it's greater than 1, that means the image is going to be larger. And if the magnification equals 1, that means the object and image are the same size. Now, taking into account the sign, if M is negative, that means the image is going to be inverted. If the magnification is positive, that means the image is going to be upright. Now, on the AP Physics 2 formula sheet, we just see the absolute value, so we're going to need to make sure that we know how to apply the positives and negatives for image, object distance, image height, and object height, and magnification. So let's go through an example problem that targets that. So we have an object that's placed 15 centimeters that's inside the focal length of a concave mirror. And it tells us the image height is 22.5 centimeters tall when the object is placed 10 centimeters in front of the mirror. So first thing we're going to do is draw a ray diagram to locate the image. So we draw our ray diagram, and we can see that the rays of light that we draw are going to diverge on the same side as the object. So we're going to extend those rays of light back behind the mirror to locate that image is going to be a virtual and larger image. Second thing we're going to do is find the value of the focal length of the mirror. So naturally we'd go to the focal length equation, which is our lens mirror equation. But the problem in this equation is we don't know the image distance and we don't know the focal length, so we have two unknowns. So what we're going to do is we're going to use our magnification equation, the two pieces of the image over object distance and image height over object height. And we know three of those four values, so we can rearrange this equation to solve for what we're looking for. So what we're looking for is the image distance. So we can rearrange that equation and solve for image distance. And then we can substitute the values in to solve for the image distance. And that gives us that the absolute value of the image distance is 15 centimeters. But now here's where we need to apply, knowing that it's a virtual image. The absolute value is 15 centimeters, but the actual value, because it's a virtual image, is negative 15 centimeters. So we need to use that in our lens mirror equation, that it's negative 15 centimeters because it was a virtual image that forms. So we can bring back our equation for the lens mirror, and then we can solve for the focal length by doing the inverse of each side, which just gives us f equals the inverse of the 1 over SO plus 1 over SI. Then we can substitute our values in for object distance and image distance. Remember, image distance has to be negative since it's a virtual image. And then we can evaluate that, and we get that the focal length value is going to equal 30.0 centimeters. So we want to make sure that that answer makes sense. Well, if it's placed 10 centimeters in front of the mirror, well, that's in between the mirror and the focal length. And we also got a positive value, which means that we have a real focal length, which the rays of light actually pass through, which is the case. So this is an introduction to curved mirrors, concave and convex, using the lens mirror equation and magnification equation. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @Cavi Coaches.